So today I would like to make some formal computation in fluid mechanics and kinetic theory. I am going to assume that everything is smooth, just to avoid doing a technical computation and to avoid making very long computation. So let me start with a Lagrangian. Versus Eulerian coordinates. Okay. So assume that I have a trajectory, or I have trajectories. So for each z in RD, I have a trajectory t goes to phi of t z. And assume that it is smooth of class C2, for instance. So the velocity of, and I assume that phi at time 0 is z. Okay. So I take a particle which is sitting at time 0 at a point z, and assume that the particle is moving. And I call phi t of z the position of that particle at time t. Then the velocity is t dot of tz, which is the partial derivative with respect to time of phi at tz. So here is a particle at time 0. It starts moving, and at time t, it is here. Now I look at the collection of all these particles, and I take a point. Instead of following the particle, I take a point W. And I want to write the velocity of the particle arriving at W at time t. So the velocity, if I call W t, the velocity of the particle passing through W at time t. Then I have a relation phi dot of t z equal to W of t phi of t z. And my initial condition is phi of 0 z equal to z. So assume that W is a Lipschitz, for instance. Then this OD has a unique solution for a short time. Assume that W is Lipschitz and bounded. Then this OD has a unique solution for all time. Right? So if we want, we can assume that W is of class C1 and of compact support, and this will imply that W is Lipschitz and bounded. Now, I am talking about a collection of points. consider a collection of points and call F naught the distribution. So F naught is defined from Rd to 0 plus infinity. So F naught of Z expresses the density, the probability to have a, let me normalize. What is important is I want F naught of Z to be finite, but let me normalize the mass to be, the total mass to be 1. So F naught of Z dz is telling me the mass of the particle around Z. So this is the distribution of my system at time 0. My system is evolving, so its distribution will change over time. So that is given. Now, call Ft. This is the push forward of F naught by phi t. Okay, so more precisely, what I want to define is the following. I want to define Ft such that when I integrate over a set B, Ft, W, dW, this is the same thing as integrating over phi t inverse of B F naught. So this is what the push forward mean. And if everything is smooth and one-to-one, this is equivalent to Ft of phi t of Z. Determinant of the gradient of phi t of Z is F naught of Z. So this is a familiar change of variable we are familiar with, which is saying that phi t is pushing F naught forward to Ft. So let me write what this means mathematically. It means the integral over Rd of L of phi t z F naught of Z dz equal to the integral over Rd of F L of W F T W dW for every F which is of compact support and of class. It doesn't matter to say that it is of class C0 or class C infinity, because by approximation, all these things are equivalent. And you can notice that what I wrote there is the same thing as what I wrote here if I replace L by the characteristic function of B. So that is my definition of, we're calling the definition of push forward. So let me derive the continuity equation. For F. So in Eulerian coordinates, if in Lagrangian coordinate, if phi is a one-to-one, then this is the continuity equation for Ft. So the one I would like to derive is not going to take into account whether or not phi is 1-to-1. It will go from this formula, call it 1.
Why don't you simply define a decomposition at 0, phi, d? It's not the case.
Why don't I do what?
Define ft dot as the composition of f0 with phi d dot. Isn't it the same?
No, I don't know that I have a compressible situation. So you are saying, why don't I say that this is 1?
As 1, yes, you have to take into account this, okay.
Yes. So if you make a change of variable, if you make a change of variable w equal to phi of tz, then you see that this is exactly what you get with the Jacobian.
You define it by right.
Yeah. So by 1, d over dt, the integral over rd of L of phi tz f naught c dz equal to d of dt, d over dt, the integral over rd of L of w ft w dw. Now, if everything is smooth, I can pass the derivative inside and get that the integral over rd, the gradient of L phi tz, inner product phi dot tz f naught of z dz is the integral over rd of L of w, the partial derivative of f with respect to time at tw dw. So this should hold for every L. Now I'm going to replace 5 dot by this. To write that the left-hand side is the integral over rd of.
What about the gradient?
Which gradient?
There's no gradient in L in the right.
No, I am differentiating with respect to time. So I have a derivative of this, which is.
The last equation. L, how about L? No gradient in L?
L is independent of t. So the derivative of this is here.
Why is this equal to the other one? There is a gradient of L.
Shouldn't that be plus in between? Second line, there's an equal sign. I thought that should be a plus.
So I start by this. These two things are equal. Therefore, the derivative is equal.
Yeah. So this is what? The below what you... So you are deriving the below, this is equal to this. And this is equal... Okay, and now...
Yes. So I should have written this is equivalent to.
Yeah. Yeah, I thought it was a continuation of the equation.
Yeah. So I am going to replace phi dot by w, and I have L of phi, inner product w, phi, f naught, dz, equal to the integral over rd, L dtf dw. Now, I am going to use 1, where I replace L by L tilde of W equal to gradient L of W of yes, L tilde of omega is gradient L of omega, W of omega. So if I do that, we see that the left-hand side is the integral over RD, gradient L, W. There is a T missing here. W of T. Let me write omega. Omega ft of omega d omega equal to the integral over RD of L of omega dt of f t omega d omega. Okay, so this is equivalent to that, which is equivalent to this. Now I integrate by part. If I integrate by part, the left-hand side is the integral over RD of negative divergence of f w multiplied by L, and the right-hand side is L dtf, and this should hold for every L. So saying that these two terms are the same for every L is equivalent to dtf plus divergence of f w is 0. And that is the continuity equation. Yes?
The last line, the t should be inside the parentheses, right? Not the time derivative of f.
Yeah, side difference.
You said in the last?
So you put
The last line, left side.
Left side?
Yes, ft.
Yes. Okay. So I have written that this implied that, but the converse is true. Because if I have that, I can go back up to here. Now, it will imply that these two things are the same up to a constant. I look at what happened at time t equal to 0 to see that the constant is 0. And so it implied that this holds. Okay. So we have not lost any information. And what will be used often in the literature is this continuity equation. If you have a system whose distribution is ft and velocity is w, then it satisfies that continuity equation if everything is smooth. One can show a stronger result, which is due to Ambrosio, Gigli, and Savary. Even in lack of smoothness, you still have this continuity equation, which is satisfied. So here, what Ambrosio, Gigli, and Savary you have no smoothness needed. assume that you have a path of T goes to the set of probability measure mu T, the set of probability measure of bounded second moment. And so here, mu T may be singular, it may be absolutely continuous with respect to Lebesgue measure. It is general. All you impose is the second moment is finite. Assume that it satisfies the following regularity property. The Wasserstein distance between mu T and mu S is smaller than the integral from T to S of A of tau d tau for some A in L2 of 0T. Okay. So I am going to come back to the Wasserstein distance. I haven't really defined it. You can guess what it is. It is a Monge cost when h of z is z squared. So assume that you have this property, which if it was not an integral, I'll be saying that this path is Lipschitz with respect to the metric W2. But here I am posing something weaker than Lipschitz, which corresponds to W11. So if I had the Sobolev norm here, this will correspond to, W12, because I take A in L2. Then there exists W, a Borel map from 0T cross RD to RD, such that yes. So it is in. So what I should have said, that T is less than S, and so this implies that A must be non-negative because the left-hand side is non-negative. Then there exists a Borel field such that this continuity equation holds in the sense of distribution. Holding in the sense of distribution, I mean, if you look at this, the derivative of f with respect to t does not exist. The divergence of this doesn't exist because this is not differentiable. So in the sense of distribution, I'll be saying that it means that this holds. So it means that the integral such that the integral over RD of gradient L W F dW. So my F is now mu. So it will be mu T dW equal to the integral over RD. I am going to integrate this by part. Negative, the derivative of L d over dt, the integral over RD of f of L d mu t for every L. So you see that here everything makes sense if I know that the integral from 0 to t, the integral over RD of W square mu t dW d omega dt is finite. So if I know that this exists, when I take any L, which is of class C1 of compact support, this is bounded. Therefore, that integral exists. And this integral without dt exists. And so I am saying that this is differentiable and the derivative equal to that. And this has to hold again in the sense of distribution. Saying that it holds in the sense of distribution is I integrate, I multiply by test function alpha of t and integrate both sides. So if I want to write the complete thing, it will mean that the integral over Rd, the integral from 0 to t dt of mu t dw, and here I will have L of t w plus gradient L of t w inner product w of t w. This equal to 0 for every L, which is of compact support of class C infinity in 0t cross Rd. And you see that now everything makes sense. This is in L infinity. That is in L infinity. This is in L2. The product is in L infinity. And so I integrate with respect to a probability measure. And so everything makes sense. That is the definition in the sense of distribution. So an example. The example will be very related to what we're trying to do tomorrow and on Monday. Example. A fixed point problem and PDE. So what I want to talk about later is the nonlinear inhomogeneous Fokker-Planck equation. So let me start with the linear homogeneous Fokker-Planck equation, which is something simple, very well understood. And that will be a good example to illustrate that relation with PD. So the linear Fokker-Planck equation. Given F naught from Rd to 0 plus infinity, probability density, find F from 0 infinity cross Rd to 0 infinity, such that the partial derivative with respect to time of f is the Laplacian of f. This is the heat equation, plus the divergence of f multiplied by z. Okay, so this is f of tz equal to the Laplacian tz plus the divergence of f of tz multiplied by z with the initial condition f0 equal to f naught. So observe that the Laplacian of f equal to the divergence of f, the gradient of log of f. Okay? Indeed, if you compute the gradient of log of f, you get the gradient of f divided by f. And you multiply this by f, you are left inside with the gradient of f. You apply the divergence, and you get the Laplacian. Therefore, I can write my equation in the form dt of f equal to the divergence of f gradient log of f plus z. Which I can also write this way. I can put a negative inside. And that equal to 0. So if I compare that equation to this equation, it is telling me that the velocity, I didn't want to erase this. It is telling me that the velocity, W, depends on f, tz, equal to, let me remove the tz, equal to negative gradient of log of f plus z. So meaning plus identity. Identity of z is z. Okay, and that is Hooke's law, which says that for a certain material, its constitutive relation is characterized that by the relation between the velocity and the density. Okay, now this is a fixed point theorem because of the following fact. My velocity depends on f. So consider the following problem. Consider the operator f. This is an operator. So you want to solve, having this velocity, solve phi f dot of tz equal to w f of t phi f of tz phi f of t of 0 z equal to z. Okay. So for each f given, f which is defined on so given f defined from 0t cross rd to 0 infinity, solve this equation. And the solution, the flow I will find depend on f because my velocity depends on f. Now, set g at time t to be the push forward of phi f time t, the push forward of f naught. This is a definition. I have a flow. I have a distribution at time 0. I can construct a distribution at time t. We want to solve the fixed point. Solve the equation f t equal to phi f t push forward F naught. This is a fixed point theorem, and so my PD is equivalent to finding a fixed point to that problem. So if F are associated G, and I want to know if there is I can choose F in a suitable way so that to F I will associate F. The nonlinear kinetic Koffer-Planck will also be the fixed point theorem, but it will be way more complicated than this one. So next, let me introduce the Fokker-Planck operator. So this is an operator which to a function associate another function. So fix P operators, because I will have several of them. Fix P bigger than 0. And to each P, I will have an operator depending on P. Given F from RD to 0 plus infinity, the average of F, I define UF, is the integral over RD of V of F of V dV. I define the variance to be the integral over RD of V minus UF square F of V dV. And the temperature is 1 divided by D, the variance. Now, having that, I can define given F and G from RD to 0 plus infinity, I can define L of Fg. That will be the Laplacian with respect to the V variable of F of G plus the divergence. I am writing the V variable because later I am going to also introduce X variable. The divergence of G, V minus UF divided by theta F. And I am going to multiply this whole thing by theta F to the power P. P greater than or equal to 0. And so when P equal to 0, you see that when P equal to 0 and the average is 0, you see that this corresponds to the linear Fokker-Planck operator I defined earlier. Now, the Maxwellian mu theta of V is defined to be 1 divided by 2 pi theta square root to the power D exponential of negative V minus U square over 2 theta. And MF will be by definition MUF theta F. So make the following observation. First, this is a probability density. Easy to see because it suffices to check that the integral of negative exponential of v squared over 2, 1 divided by square root of 2 pi dv. It suffices to know that that is 1 and make a change of variable to conclude that this Maxwellian is a probability density. Okay. It is also interesting to make the observation that this is related to the Maxwellian. If, note that, if I compute the log of m u theta, what I get is negative d over 2, the log of 2 pi theta, plus minus v divided by u square over 2 theta. And so if I differentiate that with respect to v, this means that I am differentiating this with respect to v, and I get negative v minus u over theta, which is what is there. So as a consequence, L of f equal to, I replace g by f. It is theta f to the power p. The gradient, the divergence with respect to the v variable of, let us compute, Laplacian of f is the divergence of f, the gradient of log of f. Okay? Because again, I said the gradient of log of f is the gradient of f divided by f. I simplify by f. I am left with the gradient of f. When I apply the divergence, I get the Laplacian. And according to this computation, the divergence of f, v minus u, f divided by theta f, this is the divergence of f, the gradient of log of mf. Because this computation tells me if I compute the gradient of log of mf, I get this thing with a negative sign. With a negative sign. Therefore, I can conclude that this is f, the gradient with respect to the v variable of log of f divided by mf. So that is what L of ff is. Any question? Okay, so let me pause here and explain why the Fokker-Planck equation is important. And then I'm going to come back to some computation. So there is a class of equations that appear in kinetic theory, very important one, the Fokker-Planck, in homogeneous nonlinear Fokker-Planck, the Boltzmann, for instance. So for this equation there was some important work of Dipernat and Lyon, which prove existence of so-called renormalized solution. I am not going to define what is renormalized solution. That was a big advance in the subject. But I am under the camera. I am washing my word. The renormalized solution, they have a problem. They don't conserve energy. Okay. So physicists expect the solution of this equation to conserve energy, and that is one of the serious drawbacks of the result of Lyon and Dipernat. So our goal when we were studying the Fokker-Planck equation is to use the Wasserstein distance to prove existence of solution for which the energy is conserved. But I want to say that we were able to do that only for p equal to 1, which means that we were able to construct this solution for a particular equation. Our technique, we don't know how to extend it to the Boltzmann equation. So this is a very restricted result in the sense that it's applied to a particular equation. But the renormalized solution still receive criticism that they don't conserve energy. So I want to make some calculation next to talk about what makes the conservation of energy occur, and something else which is called H theorem, which is very important. The H theorem says if you start with any solution, any mean, maybe not very weird solution, when time go to infinity, your solution converges to a Maxwellian. So we are going to see, at least formally, if everything is smooth. I want to make some calculation to show you that it doesn't matter what is the form of F. There are some form of L. There are some properties satisfied by the Fokker-Planck operator, which are also satisfied by the Boltzmann operator. And if you take any operator satisfying this property, the solution of the corresponding equation must have this conservation, formally at least, because we don't know how to prove them. Important property. First, if you integrate over RD L of F V dV, you get 0. It doesn't matter what F is. And we'll see that this property will imply conservation of mass. If you integrate over RD VI L F V dV, you get 0. So V is V1 Vd. If you integrate over Rd V square L of F V dV, you get 0. And this will formally guarantee conservation of energy. If you integrate over Rd L, the logarithm of F, L of F dV, you get something which is strictly less than 0, unless F is MF. So only when F is a local Maxwellian that this is equal to 0. Otherwise, it is strictly less than 0. And we will see why this, at least formally, what it has to do with the H theorem, saying that you will converge to a Maxwellian no matter where you start. So let me prove this result. They are very easy to check for the Fokker-Planck equation. They are easy to check for the Boltzmann equation. And when one is studying the Boltzmann equation, these are the main features, plus a certain scaling, which I am going to talk about soon. So 4 property plus a 5th property, which is scaling. So that will be the important equation for the important property for the Boltzmann. And to prove existence of solution, one hope that this is what matters. The specific form may not very much matter. And this is one of the reasons why we thought if you study the Fokker-Planck equation and you see how things go, maybe it will give you some idea about what happened with the Boltzmann. So proof. Let me just do this and that. Right? And you'll see the proof of this work for that and that. The integral over Rd of v squared L of f v dv equal to the integral over Rd of v multiplied by this. Now I am going to integrate by parts. Integration by parts. To get that, this is negative theta f to the power p, the integral over Rd of, let me put 1/2 here, which doesn't matter. Let me put 1/2 here. I'll have a v. I'll have f. I have an inner product with the gradient of the log of actually, I think it is better to use this formula. Otherwise, I will have to compute a few more things. So this is negative theta f to the power p, the integral over Rd. When I integrate the Laplacian, I get gradient of f inner product v. And there I get f v inner product u minus uf v minus uf over theta. dv. Okay. Now, let us make the following observation. V is a v minus uf plus uf. Therefore, v inner product v minus uf over theta f. This is a v minus uf square over theta f plus uf plus v plus uf inner product v minus uf. Okay. Over theta f. Now I integrate this, multiply by f, which means I integrate that, multiply by f, and this, multiply by f. So what can I say about that? If I look at the definition of UF, so when I was undergraduate, I have a very good friend, and when the professor is teaching an answer, this equal to what? He raises his hand, he always says 0 or 1. Because if it is not 0 or it is not 1, he will not ask you. So I can take the UF out. And then if I take the UF out, I see that. And theta f, I can take this out. And so I see that this integral is 0. Now I look at the definition of theta f. And I see that this is what? It is not 1. This is d. D by 1. Okay. So we took care of this expression. Okay, so let me write what we get. This is equal to negative theta f to the power p. And I am going to integrate again this by part. When I integrate it by part, I have negative the integral over Rd with divergence of v multiplied by f dv. And according to the calculation we made, I said this is plus the integral over Rd of v minus uf square divided by theta f of v dv. And the divergence of v is d. So this is theta f to the power p. The divergence of v is d. The integral of f is 1. So I need to say if the integral over Rd of f is 1, then this holds. No, I don't need that. Okay. So let us impose the integral of f is 1 because this is what we are going to be using. So this is negative d. And by that computation, this is D, and so that is 0.
On that step, that you crossed, you need the integral of f to be 1.
Here, here.
Yeah, because the integral of v against f is uf, and the other one is uf against the integral of f. So you need it to be 1 to get the cancellation.
Okay, yes. Okay, so now let us prove this. Call this 1, call this I, 2i, 3i, 4i, and we have 3i. For 4i, we have the integral over Rd of log of f, L of f dv equal to the integral over Rd I am going to use that formula. Theta f to the power p, log of f, Laplacian. So I will have log of f, Laplacian of f. I have log of f, divergence of something. If I integrate by part, this is going to produce gradient of f divided by f multiplied by the gradient of f. So that will give a negative gradient of f squared divided by f. The first term. The second one, when I integrate by part, I will get negative gradient of f divided by f, and multiply by f v minus uf over theta f. The f will simplify, and so I will have gradient of f with a negative sign, inner product, v minus uf divided by theta f. dv. Okay. Now let me compute something different and compare them. Set lambda to be the integral over Rd of f, gradient log of f plus v minus uf divided by theta f squared dv. Let me compute this. So this is gradient of f divided by f. let me compute this and check that it is equal to what is upstairs with a negative sign. And if I do that, I am done. We have lambda equal to the integral over RD of f, gradient of f square over f square, plus gradient of f over f, inner product v minus uf over theta with a 2 in front of it, plus v minus u square over 2 theta f square dv. That is the integral over RD of gradient of f square divided by f. And this is going to simplify with that. So I will have twice gradient of f inner product v minus uf divided by theta f. And I'm going to integrate that by parts. That will be negative 2, the integral of f, 2 over theta f. The integral of f, the divergence of this, which is d. And that will be negative 2d divided by theta f. Okay. So here I have minus 2d divided by theta f. Now I compute this. When I integrate with f, I have 1 over 2. No, there is no 1/2. There is no 1/2. I have 1 over theta f square. And when I integrate that, I get d theta f. So this one gave me 2d divided by theta f. That gave me plus d divided by theta f. And so I end up with the integral over RD gradient of f square divided by f minus d over theta f. Now, what is here? I already computed that here. So I will say similarly, we conclude that negative the integral over RD of log of f, L of ff dv. I am going to divide that by theta f to the power p equal to the integral over RD of the gradient of f square divided by f dv plus this integral. But that integral, when I computed it, I got negative d divided by theta f. when I computed this integral, this is what I got. I got negative 2d divided by theta f. There is no 2 in front of that one, so I get d divided by theta f. And I see that these two expressions are the same, equal to lambda. So this proves that lambda is negative, is non-positive. Assume lambda is 0. I want to show that we must have a Maxwellian. So hence, the integral over Rd of log of f, L of f dv is less than or equal to 0. Assume the integral over Rd 0 equal to log of f, L of f dv. So we have two possibilities. Either you trust me, or we are going to make the computation again. So you get negative theta f to the power p, the integral over Rd of f, the gradient of log of f divided by mf squared dv. That is easy, in fact, because this is the gradient. This is the gradient of f divided by f minus log of the gradient of f mf, but we saw that this is v plus uf divided by theta f. And so we see that these two expressions are the same. So the only way this can be 0 is assume f is positive. Assume f positive, and this is 0. Then the gradient must be 0, which means the log of f divided by mf must be a constant, which means f divided by mf is a constant, which means that f is a constant multiplied by mf. But both are probability density. This means that my constant is 1. And so m equal to mf. So now, what are the implications? Formal argument. Again, formal means I am assuming everything is I am assuming that everything is smooth, and I would like to show why formally the kinetic energy is conserved. Assume dft equal to LFF. So assume that F is a solution to the kinetic, to the Fokker-Planck equation. This is the homogeneous Fokker-Planck equation. Then, because of this property, we'll have that the integral over Rd of f dv will be 1. The integral over Rd of v f of v dv will be the null vector. The integral over rd. So I want to say conservation. This is the integral over rd of v f naught of v dv. The integral over rd of v square f t. So let me specify here that it is ft v f t v and f t v dv is the integral over rd f v square f naught of v dv. And we have a property d over dt, the integral over of the entropy s of f t is less than 0 unless f t is the Maxwellian. Unless f t is the Maxwellian. So I am assuming that f at time 0 is f naught, and the integral over rd of f naught of v dv is 1. So if I start with an initial condition where the total mass is 1, the mass is conserved. The first moment is conserved. The second moment is conserved. The second moment is the kinetic energy. And the entropy is increasing. So S of f, I need to write to tell what is this. S of f is the integral over rd of f log of f. This is negative entropy. So in other words, the entropy is increasing. So let us just check this and that, because the first two are even easier. We have d over dt, the integral over rd of v square ft v dv is the integral over rd of v square dt f tv dv. That is the integral over rd of v square L ft v dv. And that is 0. Because I'll have proven first that ft is a probability density. And once I know that it is a probability density, I know that the integral of v square L of ft is 0. And so we have conservation of the kinetic energy. Also, d over dt s of f is d over dt, the integral over rd of f log of f dv. This is the integral over rd. So when I have the integral of alpha of f dv, when I differentiate that, this is the integral of alpha prime of f dtf. So if alpha of t is t log of t, alpha prime of t is log of t plus 1. So if I apply that there, I'll have that this is log of f plus 1 dt f dv. The integral of f is 1, therefore the integral of dtf is 0. And so this is the integral over rd of log of f, L of f, f dv. And this concludes the proof, because we saw that this thing is strictly less than 0, instead, unless f is unless f is a Maxwellian. Okay. So now let me state the equation of the full homogeneous Fokker-Planck. So let us start with some convention. So the torus, the d-dimensional torus, is Rd divided by z to the power d. I am looking at the flat dimension torus. A from Td to Rd means two things. It means that A is from Rd to R, and A is periodic. So this means that if I write A of x plus EI, this is A of x. If I take EI to be 0, 0, 1, 0, 0, this is for I from 1 to D. So you can check easily that in that case, if you integrate A on 0, 1 to the D, A of x ds, it is the same thing as integrating on a translation. R plus 0, 1 D A of x ds. And so, by definition, this will be the integral on the torus of A of x dx. Okay? So you just check that when the d is 1, and so we have it in general. Integration by part. Let us make the computation in d equal to 1, and you can make the same computation for d higher. Assume A, B are on the one-dimensional torus, R of class of C1. Then the integral on the torus of A prime B is by definition the integral from 0 to 1 of A prime B. This is negative the integral from 0 to 1 of A B prime plus A1 B1 minus A0 B0. But since A1 equal to A0, B1 equal to B0, this is going to disappear. And so that is negative integral on the torus of A prime, B prime. Okay. So similarly, if A, B are C1 function on the torus, the integral over on the torus of A, the derivative of B with respect to Si is negative the integral of the derivative of A with respect to Si, B on the torus. So the torus is a manifold with no boundary. We are going to use that often. And let me start with some terminology. Assume f is a function from the torus cross Rd to 0 plus infinity is a probability density. So you define the special density to be rho of x equal to the integral over Rd f of x v dv. We define the conditional distribution which is f of xv equal to 1 divided by rho of x, the integral over Rd f of x. And so this is not well defined at any point where rho of s is 0, but the definition is immaterial at point where rho of s is 0. You define the bulk velocity is u of x equal to the integral over Rd of v fxv dv. And you define the temperature to be theta f of x is 1 over d, the integral over Rd of v minus uf square dv, uf of x. So we are going to consider local Maxwellian. Mf of xv, this is rho of x divided by 2 pi theta f of x d over 2 exponential of negative v minus uf of x squared divided by 2 theta f of x. So when rho is, when this is 1, then we have a global Maxwellian. Now the Fokker-Planck operator, L of f is rho of x. So this is dependent on S and V. This is rho of x, theta f of x, L, f, x, f, x, V. So something we realize when we prove existence of a solution conserving energy for the kinetic Fokker-Planck. So we try to see if the same proof will go through for Boltzmann and what will preclude the proof to go through. And we notice that in Boltzmann, you have it's called, usually the Boltzmann operator, people call it Q. We notice that this square is something causing a problem. Rho is a probability density. The integral of rho is 1. Rho square, you don't really know how to control that. And so it looks like this exponent. If you replace this exponent by 1, then you will be able to say more about the Boltzmann equation. But you will get an equation which is not physical. So the kinetic Fokker-Planck equation is d of t f t x v plus gradient x of v f of t s v equal to L of f t And as I did before, one can show formally that the total mass is conserved. The first moment is conserved. If you have enough smoothness, the second moment of the solution of that is conserved. And the entropy is strictly, the derivative of the negative entropy is strictly negative unless you have a local Maxwellian. Okay. So here is what we like to understand. Whether I write the Fokker-Planck of the Boltzmann, here is the principle. You have two mechanics at work here. One mechanics is on the s variable, and the second mechanic is on the velocity variable. This is why I'm making a point defining L on a function independent on x. Now, people consider this homogeneous Boltzmann equation where f is independent of x. And so only the mechanism on the velocity is noticeable. You can also consider this equation and become very easy, free particle. So this is how one should understand the whole thing. Let us consider the Boltzmann equation, where it comes from a system where you describe collision of particles, and then you let the number of particles go to infinity. You have particles that move freely. They collide. Once they collide, they update their velocity and then start moving freely again. So you can interpret this equation as these two mechanisms. And in fact, when you write an algorithm to solve the equation, this is exactly what you do. So I fix h greater than 0, small, and I want to construct an approximate solution. And then I want to let h go to 0 and see that the limit converges to my equation. That is a very hard thing. And if you choose the right algorithm, you get enough compactness for convergence. Note that when you write the Fokker-Planck equation, the term we are dealing with are highly nonlinear. So here you have theta f to the power p multiplied by the Laplacian of f. This product alone is highly nonlinear, and convergence of this expression is the big issues. So if I did not have this right-hand side, I'll write easily the solution to my equation. I am going to solve dtf plus v gradient xf equal to 0 for a short time. I rewrote this. I can put the v inside or outside. So I'll have the explicit solution ft of xv is f naught of x minus tv v. Okay? So all particles keep the same velocity, and they are moving. I do that for a short time, t between 0 and h. And then I want to update now applying only the velocity mechanism. So set f tilde naught of x v to be f naught of x minus hv v. Okay. And now I am going to define rho naught tilde of x is the integral over r d f tilde 0 of sv dv, and f naught tilde of sv equal to f tilde naught of xv divided by rho naught tilde of x. So for each x, this is a probability density. Indeed, fixing s, when I integrate that, I get, when I integrate f, the integral of little f dv is rho. If I divide by rho, I get 1. So now I have obtained a function which for each x is a probability density. My equation, my new equation, this partial derivative, I can write it as f1 minus f0 tilde equal to the right-hand side over h equal to the right-hand side. This corresponds exactly to that. So we want to find f1, capital F1. So we are going to look at the following. We are going to minimize. We are going to minimize over f the Wasserstein distance square between f and f not tilde divided by theta f to the power p plus the entropy, the integral of f log f. So what we show is this mechanism corresponds to that mechanism. However, I want conservation of the first and second moments. We are going to impose that we are minimizing this under the condition that the first moment, the Maxwellian of f is the Maxwellian of f not tilde. Right? So saying that two Maxwellian are equal means that is equivalent to the fact that the first and second moment are equal. The fact that you restrict yourself to this manifold, you add this extra constraint, make the problem much more difficult. From the calculus variation point of view, the problem without this constraint is an easy problem. You check lower semi-continuity of this, lower semi-continuity of that, and you get existence of a minimizer easily. Once you have this, you add this constraint, you are minimizing a functional, even if it is converse on the whole space, you are constraining yourself on a manifold. If you take a minimizing sequence, you have no guarantee that you stay on the manifold. And in fact, we wrote a separate paper to prove existence of a minimizer to that problem before we can solve this equation. Now, one last point I would like to draw is I think it is interesting to make that observation, to understand a little bit this algorithm, to understand that everything appearing there is physical. The Wasserstein distance seems like something strange, right? And why will that be more physical than any other algorithm? So here are facts. Here are some.
Just to understand, so you have an equation with a right-hand side, right?
Yes.
And then you approximate, you first take care of the homogeneous equation with zero right-hand side. And then this seems to be like a fractional step. So you give one step more to recover that right-hand side, right?
Yes.
Resolving this variational problem.
Yes. Let f not f1 be given. Let me call it fh so that it is consistent with what I have there. Let f naught and fh be given. And I am going to look at all the paths connecting f naught to fh. These paths are characterized by this fact. F at time 0 is f naught. F at time h is fh. So f, v are unknown. Okay. So saying that there is a path in the set of probability measure connecting f naught to f1 is equivalent to there exists f and a velocity v, vector field v, such that this equation is satisfied and we have this initial and terminal condition. Now, I am going to write the kinetic energy corresponding to that. The integral from 0 to h dt, the integral over rd of v square f, so it will be v of t x square f of t x ds. So the kinetic energy is 1/2. Okay, so I take an arbitrary way of connecting these two functions. I write the kinetic energy corresponding to that. Now I minimize over all W and F. Among all the possible connections satisfying this terminal and initial value condition, I want to minimize. Then the minimum is the Wasserstein distance square between F naught, FH, divided by H. Okay. So if you come back here, I realize that I made a mistake. It should be H here. It should be theta F to the power B. This is what it should be. So if you come back there, you see that what my algorithm is doing, it is adding the kinetic energy and subtracting the entropy. And it is minimizing this action. Under the constraint that, under the additional constraint that, so I am minimizing an action which is from 0 to H, F, W, F, W. And then I am minimizing under FH, under the constraint that FH, the Maxwellian of FH, is the Maxwellian of F0 tilde. Now, written this way, everything makes sense physically. I am adding a kinetic energy to, I am subtracting an entropy from a kinetic energy. I am minimizing that action on a manifold, and I am getting the next solution. And it turned out that this corresponds to the discretization of that problem if I did not have the derivative with respect to x. I will stop here.